Today we'll be looking at base A logarithms. Our objectives will be to define base A logarithms, to use inverse properties of logarithms to solve equations with logs base A, and to practice solving equations with logs base A. First, let's define a base A logarithm. The log base A of x is equal to k if and only if x is equal to a to the k power. Now that's your formal definition, but let me also give you our inverse properties of base A logs. The log base A of a to the x is equal to x, and a raised to the log base A of x is equal to x. Once again, I need you to notice that in these inverse properties, we look for those bases to match, and we'll get the exponent. Here, this base matches this base, and so you get that log. Hopefully you're recognizing that this is very similar to what we did before, with common logs where our bases were 10, with natural logs where our base is e, and then today we'll be looking at any base. So let's see if we can solve an equation with a base A log. If I have a log base 2 of x is equal to 5, the first thing I'll need is the inverse property of logarithms. Because I see a log here, my step will be to exponentiate. I will use this whole side as the exponent over here, and this side as the exponent on the right side. The base I'll use is the base you see right there. So I'll write 2 raised to the log base 2 of x is equal to 2 to the 5th power. This is exactly what you see in your inverse property. This base is the same as this base, so we get x on the left-hand side is equal to 2 to the 5th power. We simply need to use our calculator if you need to raise that to the 5th power, and you get x is equal to 32. Let's look at another one. This time I have 7 times log base 6 of 4x plus 5 is equal to negative 2. Let me once again give you the inverse property that we'll need to solve this. Let's begin by subtracting 5 from both sides. So I get 7 times log base 6 of 4x is equal to negative 7. We'll now divide both sides by 7, and I get log base 6 of 4x is equal to negative 1. We're now in a position to exponentiate, and we'll use 6 as the base for both sides. So that gives me 6 raised to the log base 6 of 4x is equal to 6 raised to the negative 1 power. Over here, this and this are the same, so on the left-hand side I'll get 4x. Remember those negative exponents we've already worked with? When we have 6 to the negative 1 power, remember that's just 1/6, and that's why I've written this here. We now need to divide both sides by 4, and if you need to grab your calculator to do that, that's fine. But we get x is equal to 1/24. Let's continue, but this time our equation will be 3 times 5 raised to the x power is equal to 125. Notice this time you do not see the word log, but we have an x in the exponent. That's our indication that we'll be taking a log. The inverse property we'll need this time is log base A of a to the x is equal to x. Let's begin by dividing both sides by 3, and I get 5 raised to the x power is approximately equal to 41.66667. I'm now ready to take the log of both sides. But a log base what? Well, because this is a 5, if I take a log base 5, then I'll be able to get this exponent out, and that's what I'm trying to do. So a log base 5 of 5 to the x power is approximately equal to a log base 5 of 41.66667. Because these match, on the left-hand side I'll get x is approximately equal to the log base 5 of 41.66667. Now at this point we have hit a brick wall, because on our calculator we can calculate a natural log and we can calculate a log base 10. But there is nothing that we have looked at yet that allows us to calculate a log base 5. And believe it or not, it turns out that we really can't do a log base 5 on our calculator. But we can slip past this, and let me show you how. We'll introduce what is called the change of base formula. And what it says is this: if you have a log base A of x, you can rewrite that using any base you choose, as long as you choose the same one for both of them. And you'll take the log of whatever's out here becomes the top, and the base becomes the denominator. So let me show you an example of how that would work. If I wanted the log base 2 of 5, I'm going to choose to rewrite it using a base 10 because I can do that on my calculator. So that's the choice I'm always going to make right here. And then all it is take the log base 10 of this divided by the log base 10 of this. Well, you can do that whole step on your calculator in one fell swoop. And when you do, you get 2.32193. Now let's go back to our problem and see how that helps us. Over here we have the log base 5 of 41.666667. What we want to do then is calculate that as x is approximately equal to the log base 10. This time you don't see it written, but it's an understood 10 of 41.666667, and I need to divide that by the log base 10 of 5. Well, grab your calculator and do that, and you should get x is approximately equal to 2.317394. Now let me just give you a word of caution on some of these. If you actually calculate the log of this and write it down somewhere, and you calculate the log of this and you write it down somewhere, and then you come back and divide, you may find that we have a little rounding error out here. Now we should be exact at least through 4 decimal places, probably 5. But let me just say to you, when I get this, if I get 9.4 but you say I get 9.3, it may be that you are doing a little bit more rounding than I'm doing. Let me tell you how I would enter this one on my calculator. I would literally enter the log of 41.666667 close parentheses divided by the log of 5 close parentheses, and let my calculator carry those numbers as far as it can. That will give me the most accurate answer that I can get here. Let's look at one more then. This time I have 4 times 3 to the x power minus 3 is equal to 13. Our inverse property we'll need is log base a of a to the x is equal to x. I'll start by adding 3 to both sides, and then I'll divide both sides by 4. I'm now in a position to use the inverse property of logs on the left-hand side. Notice, I see an x as an exponent, and I don't see the word log. Therefore, I will take a log base 3 of both sides. Base 3 because that's what the base is right here. If I do a log base 3 of this side, I also need to do a log base 3 of the right-hand side. These match, so on the left I'll get x. And then once again I'm back to I have a log base 3 of 4. Well, that's just a number, but I'll have to use the change of base formula to find it. Let me remind you what that is. You do the log base 10 of this as the numerator and this as the denominator. So I'll get x is equal to the log base 10 of 4 divided by the log base 10 of 3, which once again I can do that on my calculator, and I get 1.261860. And I just noticed I didn't do that as an approximate, and it should be. So approximately 1.261860. Practice a few more of these logs until you get more comfortable with them, and let me leave you now with my thought for the day. Do what you can with what you have, where you are. Have a great rest of the day. I'll see you again soon. Bye-bye.